Okay, so let's continue our study of connectedness with the following theorem. This is saying what happens with the union of connected sets. Notice that we have here, when it says the union, it doesn't mean the finite union. So it's not necessarily A union B. It could actually be an uncountable union. Okay? Excuse me. So the union of connected sets sharing a common point P is connected. So how are we going to prove this? Hypothesis, we have a bunch of connected sets and they share a common point. So let's see here. So for each alpha, let's have for each alpha, S alpha is a connected subset of M, some metric space M. Now, how do we interpret this part here about sharing a common point, P? Right? Well, that means the intersection of all of those S alphas is non-empty. Say there exists P in M such that P belongs to the intersection of S, all the S alphas. Right? So P is a point that's common to all of the S alphas. What's the claim? The claim is that now I'm just going to call the union of the S alphas S. And the claim is that S is also connected. Okay, and I have a little sketch here. In this case, I've got three, I just have three sets here. Let me kind of highlight them for you. This would be one set. This would be another set. Right, and then this would be a third set. But you could totally have uncountably many sets, right? And you can imagine having just uncountably many sets. And the only requirement is that there's some point that is in each and every single one of the sets, right? So we just want the intersection to be non-empty. Okay. But for the purposes of my picture, I just drew three, so it'll be really easy for us to see. In fact, we could put our point P, right here in the middle. Yeah? Okay. So, let's get to our proof. So our claim is that S, which is the union, is also connected. So S, for us, would be this entire subset of our metric space, right? And we want to show that S is connected. First thing we're going to do is we're going to say since the intersection is not empty, let P belong to S alpha. Although we actually don't need that because we included that in our hypothesis, right? So let's change this to step number 1. We're going to do a proof by contradiction. Usually with these proofs usually, not always, but usually, you want to prove something is connected. A profitable way to approach that is to assume that there's a separation and get a contradiction. Okay? So suppose S is not connected, then, now this is using one of the definitions, one of those 3 definitions. If S is not connected, then there's a subset of S, which is clopin and proper. Okay? So S is equal to A, disjoint union, A complement. A is clopin, and in S, and A is a proper subset of S. Okay, so that's the setup. Now I'm going to change all of these numbers because we did some restructuring. Okay, let's look at number 2. Without loss of generality, since P belongs to S, P is either in A or it's in A complement, right? So remember, so I've got here A is blue and A complement is purple. So let's see here. So we're saying A is just going to be this top half, right? And then A complement is going to be the bottom half. Now, P is a point that is in the intersection of all of the S alphas. So P belongs to S, which is the union of all the S alphas, right? So from here, since S is equal to A, disjoint union A complement, P belongs to A or P belongs to A complement. Now, without loss of generality, we may as well say P belongs to A. Why is that without loss of generality? The reason why is because suppose P belongs to A complement. Then all we do is go back, turn this into A complement, and now the complement of A complement is just A, right? And then A complement clopen, A complement proper. Everything is the same. It doesn't matter which you call A and which you call A complement. The point is that they're complement sets to each other. Okay, so without loss of generality, let's just suppose P is in A. So I'm going to sketch, add to my sketch, my little point P. Okay, so P is in the blue part. Now, for each alpha, S alpha is equal to S alpha intersect A, disjoint union, S alpha intersect A complement. So let's fix a specific. I just kind of want to show you how this works. So here we go. And remember, we've got our set split into, this is the A part is the top part, and A complement is the purple, right? So our S alpha can be written as the part of S alpha that is in A, which is S alpha intersect A, and the part of S alpha which is in A complement. Disjoint union S alpha intersect A complement. So that's what we mean, okay? Now, we still have our little point P here. Okay, notice that S alpha intersect A is open in S alpha, right? And S alpha intersect A complement is also open in S alpha. Why? Because we said A is clopen, right? So if A is clopen, that means it's open and the complement is also open. And this is in S alpha. So let's see here. So A is clopen in S, and remember, the inheritance principle is going to give us that the intersection of those open sets with the smaller subset is how you get the open sets in your smaller subset, intersecting that set with open sets in the ambient space. Okay? So we have this fact that for each alpha, S alpha can be split up into these two disjoint sets. Now watch this. If P is in A intersect S alpha and S alpha is connected, that means that S alpha has to be equal to this part right here. Otherwise, we would have a separation. So remember, if you have a connected set, so this is connected, and if I can write it, if I can express my connected set as the disjoint union of two clopen subsets, one of those better be the empty set. Because I can't have two disjoint clopen proper subsets, right? Because that gives me a separation. If my set is connected, there does not exist a separation. So one of these must be the empty set. And since P belongs to A, P is going to be in S alpha intersect A. So this has to be all of S alpha, and this has to be the empty set. Yes? Now, what does that mean? That means that S alpha is actually a subset of A. So looking back at the picture, it turns out that no part, right? It turns out that no part of S alpha was in A complement to begin with. Everything's in A, right? And if that's true for every alpha, that means that S is a subset of A. So let me scroll down here. Okay. So S is a subset of A. And what does that mean for us? That means that A complement is an empty set. So it turns out that there was no, right? There was no A complement. S is all of A. So we get a contradiction. We get a contradiction to A being a proper subset of S. So I'm going to put up here contradiction to A being proper. So there does not exist a separation of S. So S is connected. All right. Now let's introduce a topic that is similar, a concept that's similar to connectedness. It's called path connectedness. Now, path connectedness intuitively is easy to grasp in terms of a geometric image, right? But don't get stuck and don't get caught just thinking about the geometric image sometimes. So in other words, understand that having a path is bigger than just being able to draw right points, right? So using our visual intuition doesn't describe the whole situation, but use it to your benefit. So exactly, we got to start off with giving a good solid definition of path. What is a path? Well, a path in a metric space is a continuous mapping from some interval AB to the metric space M. So I should put in here metric space M. Continuous mapping gamma from some closed interval in R to M. Now M is path connected if for any 2 points P and Q and M, there's a path from P to Q. So, like here would be a picture if we were to draw a picture of it. So we're saying, suppose this is M, and suppose this is P, and this is Q, then there exists some map gamma from some closed interval A to B such that A is sent to P, B is sent to Q, and all of the points in between are continuously mapped and are continuously sent to points in M. So you could say that you're continuously deforming this closed interval into the equivalent of a closed interval in M, right? So that's the idea. Okay. So we've got two facts. Fact number one. And here's fact number two. Fact number one. If a set is path connected, it is connected. So being connected is stronger than being path connected. Why? Because some sets are connected, this is fact number two, but they're not path connected. Okay, so if we were to draw, because we love this, if we were to draw this picture, this is going to be all subsets. And then you have this little small speck here. That's going to be the set of connected subsets. This is my Venn diagram. Subsets. And then inside there, teeny tiny path connected. Yeah. Subsets. So every path connected subset is connected. Some connected sets are not path connected. Okay. So let's actually go ahead and prove that path connected implies connected. So we're going to do a proof. Now, what would be our hypothesis? Hypothesis is M is path connected. Claim M is connected. Proof. Well, what we're going to do is we're going to show that you can't have a separation. So suppose M is, so say here's A and here's B, and M is equal to the disjoint union of A and B, right? Now, suppose A and B are, let's say this is a separation. As soon as we say it's a separation, then number one, disjoint union of A and B is equal to M. Number two, A and B are both clopin. Number three, A and B are both proper, right? So there exists some point P in A and some point Q in B because A and B are both proper subsets. Now, M is path connected, so we know there's some gamma. So here's A, here's B. There's some gamma that's continuous that maps this closed interval AB to P and Q. So A mapped to, let's see here, so A is mapped to P, and B, let's say, is mapped to Q. And the points in between are in a continuous way mapped. So we're starting here and somehow continuously we end up here. Did you notice how I went from blue to pink and I wanted to blend them in a continuous way, so I chose purple? Because I think blue and red together make purple, right? So if this were like a professional video, then I'd have like a rainbow spectrum so that the blue would fade to the pink. But this is not a professional video. But so I just did purple all the way. But you get the idea. You get the idea. Now look. What are we going to have? We automatically will have a separation in AB because the key is that AB is connected. Yeah? AB is connected. Gamma is continuous. So gamma takes the pre-image of open sets is open because gamma is continuous. And also the image of connected sets is connected because gamma is continuous. So we should easily be able to say, hey, what is going to be a natural separation? What separation would we get just from the picture? We've got to have the points that are mapped to A under gamma versus the points that are mapped to B. Right? So we kind of naturally under gamma. So my picture is getting a little crazy here. Let's go ahead and write this out. Notice that or did I already write it? Oh, I already wrote it up here. The pre-image of A, that's the green part over here. Disjoint union with the pre-image of B, that's the orange part over here, is a separation of AB. Why is it a separation? Well, again, it's going to be non-empty. So gamma pre-A, gamma pre-B are both non-empty. Why are they both non-empty? Because P belongs to the preimage. A belongs to, wait. Let me make sure I'm not confusing myself. M is equal to this. So the points in AB that are mapped to A, yes. A belongs to the preimage of big A under gamma, and B belongs to the preimage of big B under gamma, right? Because gamma of A is equal to P, which belongs to A, and gamma B equals Q, which belongs to big B. Okay. So they are non-empty, which means they are proper. Clearly, AB is equal to gamma pre-A union gamma pre-B, right? If you have a point, let's see here, if X belongs to AB, then gamma of X belongs to let's see here, if X, then gamma of X belongs to M, right? But M is equal to the disjoint union of A, B, right? So gamma of X belongs to A, or, and this is an exclusive or, gamma of X belongs to B, right? So X belongs to the preimage of A, or X belongs to the preimage of B. Okay. So the last thing we need to do is show that these are both open, and they will be open because A is open in M, B is open in M, so the preimages are open in AB since gamma is continuous. So AB open in M and gamma continuous imply gamma pre A, gamma pre B open in AB. So they have to be clopen because we've got a disjoint union, right? So if they're open, then their complement is also must be closed. Yeah, so we've gone through that argument, so I won't repeat that in all of its gory detail again. All right, so what do we think? We get a contradiction to the fact that AB is connected. So it must be that M is connected. Right? So in other words, this part here, there exists a separation. It is not the case that there exists a separation. And so all of this would be, I would squeeze it down here at the bottom here, but we didn't have space, so that's the conclusion of that proof. Now, we have a question, natural question. What sets are guaranteed to be connected? You should also be asking yourself, what sets are guaranteed to be compact, right? What sets are guaranteed to be complete? So these are things to be thinking about as you prepare for the next exam. So here we are. What sets are guaranteed to be connected? Well, we know the continuous image of a connected set is always, going to be connected. Another way to think of it, or another way to get connected sets, is to look at the closure of connected sets. So this is another important theorem. Let's go through this theorem. I think we'll do a sketch of this one. Suppose S is a connected subset of M. Now, remember we said that, here we are, we're looking here. Remember we said that the closure of S is the smallest closed set containing S. So and the interior of S is the largest open set contained in S. So you think of the closure of S as kind of a skin, right? It's kind of like a skin on S. What we're saying is if you have some set T that is in between, is a subset of the closure, but it also contains S, then T has to also be connected. So this is connected if S is connected and T is a subset of the closure of S and T contains S, then T is also connected. Notice that this theorem automatically implies that the closure of a connected set is connected. Okay. Now let's do our proof. If not, so what is the if not? So suppose T is not connected. So I kind of tried to draw a picture here. S is in blue, T is in purple, right? And then the closure, now this is just for the purpose, right? We know that there's not really a gap. Looks kind of like a pear, but perhaps I'm just hungry. Okay. So let's say the closure of S is in black. Again, this is just a sketch for us to be able to tell to get our sets, keep our sets clear. If T is not connected, then there exists a separation of T. So we've got A and B cloping in T, right? Proper subsets. Now let's get ready to put in to indicate our A and B. Now T is purple, so I'm going to take so here we go. So this is my A, this is my B, and I'm saying T is a disjoint union of A and B. So I have a separation. A and B are proper, they are cloping in T, and all of that. Now what? What do we do? What's the problem with this? Well, what does it mean to be cloping? So A open in T implies there exists U open in M such that A is really U intersect T. This is due to the inheritance principle. So according to the inheritance principle, and we can do it for A and B, there exists U and V such that A is U intersect T and B is V intersect T. So now let's go ahead and sketch our so here's U and here's V. Okay. Now remember, S is connected, right? So U intersect S is going to be open in S, and V intersect S is going to be open in S, right? So U and V open in M implies U intersect S is open in S and V intersect S is open in S. But what is U intersect S? U intersect S is just going to be A intersect S. Why? Because S is a subset of T, right? So I'm just going to sketch it right here. So remember, A is U intersect T, right? But S is a subset of T. So U intersect S is just going to be equal to A intersect S. Sorry, U intersect S, yeah, is going to be equal to A intersect S. Okay? And we can use the same argument to show that V intersect S is what? That's just B intersect S. We're gearing up to get a contradiction. We're gearing up to show that any separation of T corresponds to a separation of S. So A intersect S is open in S. B intersect S is open in S. So we claim S equal A intersect S, disjoint union B intersect S is a separation. So why are they disjoint? They're disjoint because A and B are disjoint. So A intersect S and B intersect S are disjoint because A and B are disjoint. Is it the case that S is equal to A intersect S union B intersect S? Clearly, A intersect S union B intersect S is a subset of S, right? Why? Because if you have a point in A intersect S, it's an S. If you have a point in B intersect, it's an S. So the union of those two sets is a subset of S, right? So we just need to show that every point in S is either in A intersect S or B intersect S, okay? So let union B intersect S. Suppose P belongs to S. Well, now what does it mean for P to belong to S? Looking back at our picture, S is blue, right? So wherever P is, if P is an S, that means P is in T because S is a subset of T. And if T is equal to A union B, that means that P is in A or B. So let's go ahead and write that out. Then P belongs to T since S is a subset of T, right? So P belongs to A or B. So now we've got that P belongs to S and P belongs to A union B. So P belongs to S and A or S and B. Good, so we are done with that. So S is equal to A intersect S union B intersect S, right? And couple that with the fact that these sets are disjoint and we get A is the disjoint union. Yeah. Again, we're gearing up to show that this is a separation of S. So we've shown this disjoint. S is equal to the union of the sets. Now we need to show that the sets are proper and clopin. To show A intersect S and B intersect S are proper subsets of S. Well, how are we going to show that A intersect S and B intersect S are proper subsets? Well, let's do a proof by contradiction. So suppose they're not proper subsets. That means one of them is empty and one has to be all of S, right? Because to be proper subset, that means that you've got a point in A intersect S and you have a point in B intersect S, right? But if that's not the case, then A intersect S is all of S, or A intersect S is an empty set. So without loss of generality, so we're going to say suppose not. Then A intersect S is equal to S, or A intersect S is equal to the empty set. Without loss of generality, let's just suppose A intersect S is equal to the empty set, so that B intersect S is all of S. Yeah. So now, what's our picture? Our picture looks like this. Here's S. And remember, we had like a B. So maybe here's B. Right? We had our U and our V. Here's U. And we had V. T is this plus some A. And by plus, I mean union. Right? So T is A disjoint union B. But we're saying S is a subset of S intersect B. So S intersect A is empty. Now remember, this is a separation of T. So A is non-empty. So there exists some point P belonging to A. So that means it belongs to A, but it doesn't belong to S, right? This P belongs to T, which is a subset of the closure of S. So what does this mean? This means that there exists a sequence of points in S which converges to P. So the problem is that we've got the sequence of points in S converging to P. I did a horrible job of showing that graphically. So we've got some P sub n's. They're converging to P. But remember, A is open. So since P is in A, we've got this R ball, which is completely contained in A. So we're not going to have any points in S and that R ball. So there's no way we can have a sequence in S converging to P. So, but A is open in T. and P belongs to A, so there exists R greater than 0, such that the R ball centered at P is contained in A. Now here's the deal. Since Pn belonging to S implies Pn belongs to T, we get a contradiction. Because we would have points, we can't have points in S that are also in that R ball centered at P. So A intersect S and B intersect S are proper subsets. Of S. And again, looking at the picture, the idea is we can't have S over here in B separated from A because there are some points in the closure of S that are in A, right? So then we've got to have some points in S that are in A as well, or really close to A, right? So A can't be open and also have points in the closure of S. Okie dokie. So let's see here. So where are we in our proof? So we're trying to show that T is connected. And we said, suppose T is not connected. If T is not connected, then there exists A and B, such that A and B are clopen and T. Here I am, right? And they are proper subsets, right? And so what we said was, we said, basically that means that we will have a separation of S. So A and B give us a separation of S. Now we're in the midst of proving that it's a separation. So we've got to prove that these sets are disjoint. We've got to prove that their union is equal to S. We did that. So we proved that they are disjoint. We proved that the union is equal to S. The union of them is equal to S. Right? So we are allowed to say that S is the disjoint union of those two sets. Now we're saying that they are proper. And the last thing to do is to say that they are open. Why are they open? They're going to be open right here. Open in S, open in S. A intersect S and B intersect S are open in S because their U intersect S and B intersect S. And U and V are open in M. So we apply the inheritance principle to S. So we get a contradiction to the fact that S supposedly was connected. Right? So, one more time. If S is connected and there is a separation of T, that will give us a separation of S. Contradiction. So, must be the case that if S is connected, T is also connected. So let's go ahead and finalize that. So S equal A intersect S, disjoint union B intersect S, is a separation. This contradicts the hypothesis that S is connected. So it must be that T is connected. Right? Because when we started this, we said, let's suppose T is not connected. Right? Contradiction must be that T is connected. Okay. Now, I encourage you to read more about path connected and connectedness in section 22 of Ross. I have attached it to the homework. I think that Ross does a really good explanation of the connectedness and gives more depth. So make sure you read through those pages. What else do we have here? Let's go to, this looks like an interesting example. What is this example going to show us? This goes back to, remember our second fact? We said we had two facts about connected and path connected. Number one, path connected implies connected. So we proved that. And now we'll show that it is not the case that connected implies path connected. All we have to do is exhibit an example of a set that is connected and not path connected. Okay, and how are we going to do that? We're actually going to use our last theorem that we proved, right? Okay, so here's your setup. G is essentially the graph of the y equals sine 1 over x. Okay, now G is going to be connected. Why is G connected? G is connected because continuous image of a connected set is connected. So it's the image of the positive real axis under this continuous mapping of x sent to, so our f would be from 0 to infinity to R2. X would be sent to x comma sine 1 over x, right? So it's continuous. Why is it continuous? Because it's continuous in each component, right? Remember, to be continuous means you preserve limits. And when we're dealing with product space, we just need to be concerned about, right, a sequence converges in the product space if and only if it converges in each of the components, right? So each of the component functions is continuous. We're good to go. So G is connected. Woohoo! I've done a sketch here of G. What does G look like? G is essentially sine curve, and as x approaches 0, the frequency right, we're just getting out of control here. So a way to kind of think of it is, you know how you have just the normal sine that goes like this, and it's nice and evenly paced, and it goes on forever, right? So you're essentially taking all of that action, the fact that it's going on forever, and flipping it and making all of that back and forth happen, right? But now you are approaching this little interval here. Okay, so G, we said what G is. G is the graph of the function. K is going to be G unioned with this little bar here. Now the bar goes from here to here. So K, the points on the graph, right, plus that subset of the y-axis. K is not path connected, but K is connected. Why is K connected? K is connected because K is contained in the closure. So K connected because K is contained in the closure of G. And K contains G, and G is connected. Now, why is K not path connected? K is not path connected because you can't get from I wish I could zoom in here. I'll try my best. I'm going to use yellow. There's no way, say, to continuously get to the origin. So if you pick any point here, right, any point in G, there's no way to continuously go from G to the origin, because you'll essentially go, you'll follow the curve of G, right, back and forth, back and forth, back and forth, but it's going back and forth, and then there's no way to like continuously skip over to 0. Does that make sense? So this is our example of a set that is not path connected, but it is connected. Okay. So here's a neat fact, because sometimes it can be tricky, difficult to figure out, hey, is a set connected? Is a set not connected? Well, if we are in this special case of Euclidean space, Rn, we know that any open connected subset of U is also path connected. So remember, path connected always implies connected. So what we're saying is, if you have an open set in Rn, connected if and only if path connected. So for an open set in Rn, let's call the open set U. U is connected if and only if U is path connected. Now I just want to do a sketch to show you, just a sketch to show you how we would go about proving this. Now again, always path connected implies connected, so really we just need to show that connected implies path connected. So our hypothesis would be U is connected, and the claim is, and U is open, and U is a subset of Rn. Hypothesis of claim, U is path connected. Okay, so for the proof, without loss of generality, we can assume that U is non-empty, because if U is the empty set, then U is path connected because you don't have any points in U, right? So U is non-empty, U is open. We're going to fix a point in U, and we're going to define A. So A is the set of points Q where there exists a path, which is a continuous map, right, from P to Q. So kind of like any point you could get to via a path, that's going to be A. A is going to be the set of all points in U such that there exists a path from P to Q in U. Here's the deal. A is non-empty. Why is A non-empty? Because P belongs to A, because you can have a path from a point to itself. It's just going to be the constant function, right? A is closed in U. So let's think about this. Why is A closed in U? So in order to be closed, we want to say that if you have a sequence, if P sub n is in A, then if P sub n is in A and P sub n goes to P, or P sub n goes to Q, as n goes to infinity, then is Q in A? That's the question. All right, so let's look at a picture here. So suppose we've got some Q sub n's in A, Q1, Q2, Qn, and they're going to some point Q. Let me switch these to Q sub n's. Now remember, what does it take, or what does it take to be an A? It means that there's a path from P to Q. Q1, P to Q2, P to Q3, right? So we're saying if these Q sub n's are getting close to Q, is there also a path from P to Qn? Here's the deal. Fix a Qn, we can get as close as we like to Q. Why do we say that? Because Qn is converging to Q. Since U is open, there's an R ball centered at Q that is completely contained in U. Now there has to be some point Q sub n, let me make this really big, right, see? So there has to be some point Q sub n that is in that R ball. Now I've got a path from P to Q sub n, and then I can just create my path from Q sub n to Q. It can just be a straight line segment, yeah? So Q is in A. So A is closed in U. Now, is A open? And for very similar reasons, yes. Say you have a point in A. So say Q is in A. That means that there's a path from P to Q, right? Now, since Q is in U, we've got an R ball centered at Q that is contained in U. Every point in that R ball, we've got a path from P to every point in that R ball. We just use the composition of continuous functions. So go hop from P to Q, and then from Q to whatever your point is, X, right? You can have essentially a composition of continuous functions will be continuous. So we'll have a path, right? So if Q belongs to A, then there exists R greater than 0, such that these are the points in U that are R units away from Q. We want to know, is that also contained in A? And then we say, why, yes. And essentially the reason is because the composition of continuous functions is continuous. Okay. All right, so we will, this is it for today. I'm going to, if you haven't already noticed, I've extended the homework, the deadline for the homework.